that we're going to learn before your quiz. Do you want to remind you that your quiz is on Thursday of this week? Two main topics on the quiz is basically what's going to be from homework 1, so like integrating with natural logs, definitely I think the more involved topic that we did. And then this one that we're doing today, which is going to be integrating exponentials, which compared to integrating with logarithms, this one is way, way easier and just a lot less work. So I am going to kind of, within today's notes, also just review the derivative rules for exponentials, just so we can kind of make the connections. But basically it's 2 rules, and then I have 3 examples with each rule that we have. So the first rule that I want to look at is the integrating e to the x. And we know, first off from first semester, the derivative of e to the x is the derivative rule you like, so it's pretty easy. What's the derivative of e to the x? E to the x, easy enough. The derivative of e to the x is just e to the x. So then you can kind of conclude from that, well, if you're going to integrate e to the x, what is that going to be? E to the x, not a trick question. Often though, when you are doing these problems, like we know u sub is a thing, u sub is going to show up fairly often. Where does that u show up at for an exponential? The u often shows up in the exponent. So I like thinking of the formula just because I find it a little bit more beneficial, as the integral of e to the u is e to the u. And that u is just to remind you that when you are doing u sub, it's often going to show up in the exponent of that function. So when we're integrating with this one, I have one more slide just to remind us of this, some like properties in some ways. I chose examples that kind of match, clearly it's a different rule, but kind of to match some of the missed questions from the Unit 5 test. And so the first thing I did want to remind you of, for whatever reason, I do find that some students mix up or try to combine in their heads the power rule and these exponential rules, and we want to remind ourselves that these are different functions, so they do have different rules. The power rule is going to be used when you have x raised to a number. I know we normally look at something like x raised to a whole number, like x squared, x cubed, but it really can be when x is raised to any number. So I just kind of picked a random number with a decimal. Actually, it's not too random, that's like the approximation of e, but it's still a number. When we have x raised to a number, we can just use the power rule. We know for the derivative, that number is just going to come down in front, and then we're going to subtract by 1 in the exponent. So then when we integrate using the power rule, we know that we are going to add 1 to the exponent, and then divide by that new exponent, and then plus c. So that's what we have been doing. What I don't want you to do is whenever you see an exponent thinks it is the power rule, like the derivative of e to the x is just e to the x. Sometimes what I see, and it's very, very wrong what I see, people try to use a power rule for e to the x and do some weird stuff like x moves down in front, e to the x minus 1. Just showing you that because that is something that you definitely do not want to do. Same thing for when you're integrating e to the x. The integral of e to the x is just e to the x plus c. Don't try to turn that into the power rule because that is an exponential function, not a power function or a polynomial. So for the first example, I wanted to do a definite integral. I think I spent a lot of time at the board doing like indefinite integrals, but I did just want to remind us about definite integrals. So here is the first example, which is actually going to be a fairly easy integral to find. This is a base e, so I'm going to go ahead and use that new formula with the base e. If I'm integrating from 0 to 3, we know we're going to plug in the top number minus the bottom number after finding the antiderivative. I like to just pretend, though, before I do these problems, that this is just an indefinite integral to just kind of get those numbers out of the way. So if I'm integrating an exponential function, not all the time, so I don't want to make that a rule, but probably, most likely, your u is always going to be what you see in the exponent. Again, that's not a guarantee, but like, if you want to try something, let u be what you see in the exponent. So I have u is equal to 4x. U prime would then be equal to 4. Rewriting this becomes the integral of e to the u. Dx is du over u prime. Many of you are used to the fact now of pulling out that 4 in the denominator as a 1/4. And now we can go ahead and integrate this using our new rule. 1/4 is a coefficient. What's the integral of e to the u? The integral of e to the u is just e to the u. What was u for x? If this was an indefinite one, we would put that plus c there. This one is a definite one. So before I finish this one, I would want to make sure I go back and plug in the top number minus the bottom number. Plugging in the top number, that's going to give me 1/4 e to the 12th, 4 times 3, minus 1/4 e to the 0. Could simplify that, definitely not a lot, but e to the 0th power is 1, so you could turn that to just minus 1/4 at the end of it. Questions on that? Try this indefinite integral for me. And again, things you should be thinking of when you're looking at this, when you're integrating this, we have 10x times e to the x squared. We know we can't just integrate each part, so we know that we're going to have to do with like some u sub something to cancel some stuff out. So go ahead and try that one for me. And then I have kind of like a separate problem for the third example we'll look at. Yes?
What kind of graph would that even be? Like,
I have no idea.
wow.
The question for the homework here is like, what graph would that make? And honestly, I don't know. I just kind of made it up because I know how u sub works. So if you're asking like, what's the application of that graph? Probably nothing, to be completely honest. Let's see what it looks like.
I just want to know, like there's an x, and then there's x squared, and then x squared.
It's not that exciting. It almost looks like a really skinny cubic function, actually. Yeah. So when you're looking at these problems, again, when you have an exponential function, that u is often what you see in the exponent. So I'm going to have u is equal to x squared. U prime then would be equal to 2x. Doing my u substitution, I have 10x times e to the u. Dx is du over u prime. Definitely looks like it's on the right track. So like the x's do cancel out, and then 10 divided by 2 is going to give you 5. Careful there, not 1/5, just 5. So you're really just integrating 5 times e to the u. And then just go ahead and use that new rule. So 5 is a coefficient. The integral of e to the u is just e to the u. And then this was an indefinite one, so we'll put plus c at the end of it. I don't often go through and check my answers, like especially for the ones that we're doing kind of earlier this week and last week. Checking your answer for those quotients can just be like more time than it's worth. The exponential ones are really nice because you can check your answer pretty easily. Remember to check your answer, just take the derivative of your antiderivative, and you should end up with the original problem. And this one does work out. 5 is a coefficient. The derivative of e to the x squared is e to the x squared times the 2x. That's coming from the chain rule. C is, of course, going to go to 0. Well, 5 times 2x is going to give you the 10x. So we know that we do have the correct answer. Questions on that one? All right, last one for this rule. I want to do like a different type of question. So far, I've had several questions from people working on homework 1, needing a reminder of like what this statement means when you see it on a calculus question. So I did want to go ahead and use kind of this rule to remind us of it. So it says solve the differential equation dy dx is equal to blah, blah, blah. And it tells us the solution goes through 0, 3. This phrase, solve the differential equation, means something very specific in a calculus class. There's kind of like 2 things going on when you see that as the instruction. The first thing that is telling you to do is you basically want to go back and find the original equation. So you often have like a derivative, and you want to go back and find the original equation. So that's going to be the first thing you want to do. The second thing is you want to use the initial condition to find that constant we had of plus c. And you need to find that plus c because again, your answer is going to be what like y is equal to. So again, my thinking for this one, they tell me dy dx is equal to this 3e to the 2x plus 1. dy dx is just the derivative. So if I want to go backwards and find the original function, well, how do I move from the derivative to the original function? I need to integrate the derivative. And what was the derivative? 3e to the 2x plus 1. And we're integrating with respect to dx. After we integrate it, it has given us the initial condition, which we can then plug in and solve for c. I did choose this one just because I think there is like one tricky part to integrating it. Not that it's a difficult integral, but there are sometimes a mistake I see when people are integrating it. And the mistake I see is this first term, that 3e to the 2x, it is going to require u substitution because of that 2x in the exponent. Whereas this second one, that plus 1, that is just like an easy thing to integrate. You don't need to do u sub for it. So you do want to kind of treat them separately. So if I'm looking at this one and doing my u substitution, for this first term, we know that u is going to be equal to 2x. So u prime would be equal to 2. So if I'm integrating that first term, 3 is the coefficient in the problem, so I'm just going to carry across. Dx is going to change into du over u prime, so we'll have over 2. Again, that's coming from the u prime. What's the integral of e to the 2x? Exactly what we see, e to the 2x. And then we can go ahead and just integrate the 1. Well, the derivative of what is 1, the derivative of x is equal to 1. And then we have our plus c. What is this representing? If you integrate the derivative, then that's going to give you your original function, ry. Questions on where I came up with that antiderivative? All right, now we just want to go ahead and use our initial condition.
Mr. Brown,
Yes, go ahead. Sorry.
wouldn't the 1/2, or it'd technically be a 1/2, go to the x as well?
So no, and this is where we want to be careful. The 1/2 isn't going to go to the x that we see because that x doesn't have any u sub kind of that came with it. This might help, like technically how I'm thinking about this integral is that first term is requiring u sub because it's e to the 2x. That second term is almost like its own integral, not requiring u sub. And that's why we only want the 1/2 to apply to that first term.
Oh, okay, thank you.
You're welcome. So we're using our initial condition. So it says it's going through 0, 3. So when y is 3, we know that x is 0. So we're going to go ahead and plug that in. Looks messy, but 2 times 0 is just 0. E to the 0th power is just 1. So like all that's really just 1. So I get 3 is equal to 3/2 plus c. Well, 3 minus 3/2 is still 3/2. 3 minus 1.5 is still 1.5. A mistake some people make is they stop there. They're like, oh, I solved it. I have something that's equal to a number. If you want to be careful, solving a differential equation means your answer is an actual equation itself. Your final answer would be the original y with that c value plugged in. And so this would be my final answer. Mitchell, yes.
So where did that 3 go? Did you subtract it?
This 3?
Yes.
That came from 3 minus 3/2. 3 minus 3/2 is 3/2.
Okay.
Any other questions on that one? Yeah, Bode, go ahead.
On the triple writing, it's e to the second, and then what?
Right here, sorry. That's e to the second times 0. I plugged in the x coordinate of 0.
Okay.
And then we know that e to the 0th power is equal to 1. And that's why it just became 3/2. So that is the exponential rule that we have. The other rule that we have for an exponential is when your base is not e. So I do want to say, like, the most common types of problem that even I do, that we'll see on the AP exam, will be base e. You will sometimes encounter problems where the base is not e, which is going to have a different rule to deal with. And we'll let some people finish copying that, and I'll change the slide. So then that rule is going to be, I often call it like the A to the U rule. I do find that students often forget this rule just because it's not a common one, so let's remind ourselves of it first. The derivative of A to the x, and again, when I say A in this case, this is the base of A, that's just representing some number other than E, so it's not going to be like E to the x, it's like 2 to the x, or 3 to the x, or 5 to the x. Anyone remember what the derivative of A to the x is? There's a natural log in it. Natural log of what? Natural log of A times A to the x. There you go. So that's the rule that we have from first semester. The derivative of A to the x is the natural log of A times A to the x. Sometimes chain rule there, but that's just an x in that case, so we don't need to worry about it. So where this rule comes from is we know that derivative rules backwards just give us integration rules. So if I say the derivative of A to the x is equal to the natural log of A times A to the x, then you can imagine that the natural log of A times A to the x is equal to, well, A to the x plus c. I'm literally just taking that formula we just did and switching it around because we know that integrals are just the reverse of the derivative. Now, we'll also be honest with you. Most of the time, you're not going to see a problem that already has the natural log of A in it. Like, you're not going to be asked to find something with like the natural log of A in the problem already. How the rule will actually look and where it comes from is the natural log of A is just a number. A is a number, so the natural log of A is just a number. So you can imagine kind of this rule like an equation. If you divide by the natural log of A and kind of move it to the other side, that's where the rule is going to come from. And the rule I want you to memorize is the integral of A to the x with respect to dx is equal to, again, the ln of A was moved to the other side. It's 1 over the natural log of A times A to the x plus c. That's how I memorize the rule. Some textbooks, if you have 1 over the natural log of A times A to the x, that is honestly the same thing as saying A to the x over the natural log of A plus c. Like, those are the same thing. I guess some people like what I just wrote in purple because it looks cleaner, but that's how I can just have the rule memorized. Similar to E to the x, we often have the exponent to deal with, that is, we're doing with u sub. So if you're doing u sub, then it's easier to think of it as A to the u when you go to integrate it. Yes, Caroline?
So I just got lost there on the thus, like A.
So what I'm doing here, so like these last 2 lines, that's the rule. And like if I just want to give you a rule to memorize, I'll say, hey, memorize that. Where that's coming from is this first line, that's the derivative rule from first semester. If I say the derivative of something is equal to something else, you can just flip it and that becomes an integral rule. But we often will not write the rule this way with that awkward natural log there. So if I divide by it, that's where the rule is going to come from that you memorize. So like a short answer is like, if you don't understand like that second line, just memorize the third and fourth line and you'll be fine. Yes, ma'am.
So wouldn't it be A to the U du instead of dx?
Thank you. That rule should be if I am in terms of u, let me do correct notation and put that in terms of du. Thank you. So that's the rule that you want to know. I have one more slide just to remind ourselves to compare it to like the power rule versus the exponential rule, and then just like 3 examples with this rule, just to give us plenty of practice with it. So again, similar to what I did with e to the x, for whatever reason, again, I find that sometimes some students mix up the power rule with the exponential rule. The power rule is used when you have x as the base and it's raised to a numerical exponent. So like we know the derivative of x squared clearly is 2x. I know the integral of x squared is 1/3 x cubed plus c. That's the power rule. Where you don't want to make a mistake at is when x is in the exponent, that's going to be a completely different rule entirely. The derivative of 2 to the x would be the natural log of 2 times 2 to the x. That's the derivative rule that we have for a to the u. If I'm integrating 2 to the x, so here's going to be the new rule. It's 1 over the natural log of the base times exactly what you see, and then of course plus c. I do think there are some relationships between the two, and that's why I kind of put them side by side. So for both the derivative rule, for the power rule and the exponent one, like you end up multiplying, so it was like 2 times x, natural log of 2 times 2 to the x. Whereas for the integral, you end up dividing both times. Like you ended up dividing by the new exponent, you ended up having to divide by the natural log of 2. So there are similarities, and I think recognizing those similarities will make it a little bit easier to memorize the rules that you have. So I'm going to give you one example. I'm going to ask you to go ahead and try it on your own first, because it is going to be very similar to the e to the u rule. Try that one. Many of you could probably do that one without even showing like the u sub work. You could probably do the u sub in your head if you thought about it. Yeah, but
What was that, the very last one?
what was the natural log of 2 times 2 to the x plus 2 to the x? And so similar to the e to the x problem, when you have an exponential function, your u is often going to be found as the exponent. So u would be 5x, u prime, would be 5. Doing your u substitution, that becomes 2 to the u, dx is du over u prime. Integrating, what are you essentially integrating? 1/5 on the integral of 2 to the u du. Using your new rule, what is your answer going to look like? You should have gotten, so we had the 1/5 carry over. The base was 2, so I have 1 over the natural log of 2 times exactly what you see. 2 to the u, which was 2 to the 5x, and then don't forget your plus c. And again, many of you could probably have jumped to that from the original question without those middle steps, which is fine. That's how I tend to write the answer, because I like clearly seeing all the coefficients. But again, this answer would have also been fine if you just think of it as a single fraction. Like those two answers are completely identical. I know the first one looks longer, but it's just the one I prefer to help me see all the parts a little bit more clearly. Any questions on that one? All right, let's get a little bit weird then. There's a scary one. I have the integral of 3, and to be clear how I type that in, that's 3 raised to the 1 over x to the 4th. So all that is inside the exponent of the 3. And then all of that is divided by x to the 5th. I think this one definitely looks scarier, like there's a lot of parts kind of going on with it. Some things I hope you would notice about this one is like you do have a quotient. When you have a quotient, you got to deal with it somehow. Either typically it's going to be u sub and you want something to cancel out, or maybe you have to rewrite it, but you really just need that quotient to eventually go away. I do think there's some ways that are going to be easier to write this one to make it a little bit more obvious, and it goes to how can we rewrite that exponent so it just doesn't look as intimidating. Right now that's 3 raised to the 1 over x to the 4th. How can you write that exponent so it's less intimidating? X to the negative 4. So we know that exponents you can rewrite with a negative exponent, and like still not like the nicest looking answer, but I do think that makes the exponent look at least a little bit better. So now we want to be able to decide, like, what do we want our u to be? And there are different options. Like, some people are like, oh, well, x to the fifth is in the denominator. How about I let that be my u? Then you want to kind of think ahead. The derivative of x to the fifth is not going to cancel with what's in the numerator. Also, kind of using some other clues, when we see an exponent, often we want to at least try to let u be what we see in that exponent, which is what I'm going to do for this one. So I'm going to go ahead and let u be this x to the negative fourth. What would u prime be? U prime would be negative 4 x to the negative fifth, making sure we do the derivative power rule correctly. Doing my u substitution, that's going to become the integral of 3 to the u over x to the fifth, and then dx is du over u prime. I think most of you can kind of look at that one now as it's written. Looks weird, but what's going to happen to those x's technically? They're going to cancel out. And if you don't see that obviously, which again, those are like opposite exponents, so I hope it makes sense they cancel out. You can do some like manipulation of it. Again, that is x to the negative fifth in the denominator, so you can like move it up to the numerator, and it becomes x to the positive fifth. Either way, it will cancel out however you write it, and then you can go ahead and integrate it. What are we ultimately trying to integrate? Negative 1/4 on the integral of 3u du, and I can go ahead and just use that new rule. Negative 1/4 is a coefficient, 1 over the natural log of the base times 3 to the u, where u was x to the negative fourth. And then don't forget your plus c. So again, even when our problems look scarier, like I think that one definitely can look a little bit more intimidating, we still want to kind of think about like overall strategies that we learned. And the whole idea is you want to find a u, so that when you find the u prime, things are going to cancel out and it's just going to work out nicer for you. Any questions on that one before I move to the last example? All right, that one was weird. Let's do even weirder. How about this one? A lot going on in this one. So I have the integral from 0 to the natural log of 2. Those are just numbers. I don't care, it's natural log of 2, but it's just a number. But then we do have like a whole bunch of exponents going on. So I have e to the 5x times, and to be clear of how I wrote this, this is 3 raised to the e to the 5x. So we have like some exponents inside of exponents. There's a lot going on. Ultimately, like big idea, things you want to be able to notice when you're doing these problems. This is ultimately a product. Like I have something being multiplied. We don't like products when we're doing integrals. So we want to find some way to get rid of that product. How do we often get rid of that product? We hope u sub will give us something to cancel out. First decision we have to make. I am going to kind of clearly just treat this like an indefinite one. I'm going to ignore the 0 in the natural log for now. There's already enough going on. I want to be able to pick out a u so that things cancel out nicely. Any ideas of what a good u might be? E to the 5x. So at least people in class, most people said a good u would be e to the 5x. That is the correct one. Other classes today, and you might have been thinking it yourself and just been quiet, they see that 5x in the exponent, so they think u should just be 5x. But you can quickly kind of rule that one out, because if you do u prime, you just get 5, and 5 is not canceling out any of that mess. So like that would not work for us, but e to the 5x does. So we want to go ahead and find u prime. What rule do we also need to be careful with when we're finding our u prime for that expression? Chain rule. That's e to the 5x. We want to make sure we do our chain rule. The derivative of e to the u is just e to the u times the derivative of the exponent. And again, that came from the chain rule. And now we can go ahead and do our u substitution. Again, I'm going to ignore those numbers for now. So I have the integral of e to the 5x times 3 to the u. dx is du over u prime. Looks good. That e to the 5x is going to cancel out. We no longer have that product, which is what we didn't want. And then when I go to integrate this, I'm going to go ahead and just jump to the rule. So we had a 5 in the denominator. This is the natural log of 3 in the denominator times e to the u, and e to the u was e to the 5x. Kind of a crazy looking answer.
Let's see.
Would put a plus c here, but this is a definite one, so I am going to draw the reminder that I am evaluating this from 0 to the natural log of 2. Before I evaluate it, any questions on that antiderivative? All right, so now I'm going to go ahead and evaluate it. I will say I chose this one on purpose. So like I know for me, I'm not big on simplifying. Like you plug in the top number, plug in the bottom, and you can leave your answer really, really ugly. To be completely honest, we know the AP exam is a multiple choice exam, or at least half of it is. So often you need to find a way to like match up the answer you get to one of the choices A, B, C, or D. For these problems, often to simplify your answer, you do have to be reminded of some properties of logarithms, which you probably haven't done since Algebra 2. So yes, I chose this one for the calculus, but I also chose this one for the algebra. So almost there, so let's go ahead and plug in top minus the bottom. I'm going to condense what I have in red, so plugging in the top, I'm plugging in the natural log of 2. So I do have a 5 and a natural log of 3 in the denominator. And then this is 3e, and e is raised to the 5x. And there's where the natural log of 2 is being plugged in, minus plugging in the bottom, which is 0. So I have 3e to the 5 times 0. Now, this was my test. You can leave that answer as your answer. You would receive full credit, but it's a pretty hideous answer. Also, this was the AP exam. If you went to go bubble in your choices, I can promise you that would definitely not be one of the choices A, B, C, or D. So let's just talk about this one. Like we're done with the calculus. Let's talk about the algebra of how we would simplify it. I'm going to do the second part first. That's going to be a whole lot easier. I have 5 times 0, which is just 0. Then I have e to the 0th power. Well, what's e to the 0th power? 1. So this really is just 3 to the first power, 3 to 1, which is just 3. So again, to kind of mark it on here, all of that exponent, that's really just e to the 0th, which is just 1. So I'm going to go ahead and simplify this second term as 3 to the first power, which is just 3, over that 5 natural log of 3. What's a little bit more tricky to simplify is that first part. And what makes that one a little bit trickier to simplify is this really, really ugly exponent. I'm going to go off to the right-hand side to kind of talk about how we simplify that exponent. Good review of properties of logarithms. When I see this problem, different routes you can take to simplify it. There's actually 2 ways you can simplify it. One way is to use a property that we're dealing with coefficients in front of a logarithm. And what I mean by that, looking in this exponent, this is 5 times the natural log of 2. Anyone remember back to Algebra 2 what you can do with that 5 in front of a logarithm? Sometimes the rule is written as like c natural log of a. Where can that c be moved to? To the exponent. So like this is the same thing as saying the natural log of a to the c. That's a property of logarithm that we have. Let me rewrite that so it's a little bit less messy. So again, if you have a coefficient in front of a logarithm, you can easily move that coefficient up to be an exponent inside the logarithm. So I can take this problem, simplifying it is the same thing as saying e to the natural log of 2 to the 5th power. Simplifying it some more, base e and natural logs, those are opposites, just like x squared or the square root. So what's going to happen to the e and the natural log? They cancel out. Well, once they cancel, what's going to be left over? Just 2 to the 5th. And of course, 2 to the 5th is just 32. So that ugly kind of numerator is really just 3 to the 32nd power, definitely don't know what that is, some big old number. But that will be a little bit cleaner than what we started with. Another way to simplify that one, I don't think students see this one as obviously, so like that makes sense to you what I just did, then like use it, it works. The other way to do it is this exponent 5 times the natural log of 2. Order doesn't matter when you multiply, right? 2 times 3 is 6, 3 times 2 is also 6. So you can think of this as just e to the natural log of 2 times 5. And we have a property with exponents where when we raise a power to a power, we multiply those exponents together. So I can think of this as simply e to the natural log of 2 raised to the 5th. Because again, power raised to the power, you would multiply. Natural log of 2 times 5 is just natural log of 2 times 5. Then same deal kind of happening. Once the e and the natural log are touching each other, they cancel out. And you would just be left with 2 raised to the 5th power, which again is just the 32. I show you that just because it probably has been a while since you've seen properties of exponents and properties of logarithms, but that is how we go through and kind of simplify that problem. Any questions on that one, either the calculus question or like the algebra question?
Can you simplify it even more since the denominators are the same?
Yeah, so like I left it there because that's the hard part, but probably if this was on the AP exam, they would do something like, they both technically have a 3 in common, so you can like factor out a 3, and they both have a 5 natural log of 3 in common. What's left over? 3 to the 31st minus 1. That's probably how they would write it on the AP exam. That's not the only way to write it, but there's like, I would at least hope you can get down to this stuff, like getting rid of like the extra e's and natural logs. So that's where I'm going to go ahead and stop today's notes. So I did meet my goal. You do have about 15 minutes to work on homework and ask any questions. Things that I have assigned to you, so I guess today is no longer Monday, but things I've assigned to you, you have homework 0, which was the AP review questions, and then homework 1. What's new now is I'm going to add to that homework 2. I will say if homework 1 took you a while, like I kind of expected that, that's why it took 3 days for that topic. Homework 2 will make you feel a lot smarter because you'll go through it a lot faster, or should make you feel a lot smarter because you should go through it a lot faster. Those are the ones I would probably do a priority. Tomorrow, again, is just a work day, so come with questions. Definitely do as much homework as you can so you have questions to ask. Your quiz is going to be on Thursday, and that quiz is just going to cover basically questions from homeworks 1 and 2. We do have that weird schedule tomorrow with the Wednesdays, so there is office hours tomorrow in case you wanted to meet with me for any extra practice, or if you're already planning on like doing your recovery tests, you can do that Wednesday. Or again, you can also think about doing that recovery test next Wednesday. Other than that, that's going to kind of conclude the live portion of class. If you're at home, then I guess I'll see you tomorrow, but definitely hang back if you